we want to introduce because this one will connect us to quantum mechanics directly, okay? Which I don't understand well. But anyway, you have another thing called Hamiltonian. And what is Hamiltonian? Maybe I say it again. In the Lagrangian, remember that it depends on generalized coordinates and generalized velocity, right? Hamiltonian, it depends on generalized coordinates, the same, which is qi, but the generalized momentum, which is pi. Okay, instead of the velocity, which makes sense because there are some particle that does not have mass, like the light, right? Light does not have mass, right? So how do you treat that? I think it has momentum, however, right? H bar over lambda, I forgot, right? H bar omega is the energy, then you divide it by C. H bar K, thank you. H bar K. Okay, so Hamiltonian depends on Q1, Q2. It doesn't need to be one particle, it can be a system, right? 1 trillion particle. And then for each 1, 2, 3, 4, 5, it also have X, Y, Z direction. P1, P2, and T. So this is your Hamiltonian, okay? But this is not useful yet. We want to find the Hamiltonian. How do we find it? We can find it from the Lagrangian, and it is defined by this one. Summation I, Pi, Qi dot minus L. Okay? You need to find the Lagrangian first, and then find Pi, Qi dot. P is momentum, generalized momentum. It is not the mass times velocity. It's not always equal to the mass times velocity. For example, for the light, you cannot say that it has no momentum, right? You cannot just say its mass is 0, velocity is 3 times 10 to the power 8, so it is 0. Okay? Usually it is m times v. And this is particularly important because when you do your circuit treatment, the momentum is not something you can imagine. You need to go back to use what we derived earlier. The momentum is partial L, partial Qi dot. That's how you get the momentum. Recall? Okay. Now, and then how about for equation of motion? We call it Hamiltonian equation instead of Lagrange equation, right? So it has two equations. It says that Pi dot, the change of the momentum, equals to negative partial H, partial Qi. Okay? And then the velocity, Qi, equals to partial H, partial Pi. Right? Again, you don't need to memorize. It can be on your cheat sheet, and I don't think, even if I test it in the exam, I think I will give you the equation. I cannot memorize well also. Right? But you just want to recognize that we have Lagrangian, and then we have Lagrangian equation. We also can have Hamiltonian, which can be found by using Lagrangian, and then we can have the Hamiltonian equation. Both of them should give the same result when you describe the same system. Any questions? Yeah.
So for this first part, H minus this. So
because you will use this to find momentum. It's not about mass. You need to find the true momentum and not always equal to m times qi. Qi dot, right? And you use this equation to find. Okay, particularly when you do the circuit, you need to follow this strictly. Yeah. So let's again look at the free particle, and we expect to get exactly the same result, but I just want to show you the procedure, right? So you don't make mistake. Although we are not going to apply it to the real physical system, but we will apply it later in the quantum circuit. But we might do something in the homework to practice. What is the H again? It's P, Q dot, right? I only have I assume one dimension and one particle. Minus the Lagrangian, but I found Lagrangian already. The Lagrangian of free particle is half m q dot square. So I can just write it as P q dot minus half m q dot square. But I still don't know what is P. Okay? I can use Lagrangian to do that. P equals to partial L partial Q dot, right? Maybe you forgot already. P equal to partial L partial Q dot. So what is this? Partial L is 1 over 2 mq dot square, right? This is L, right? If you forgot, this is L. I know it's a little bit confusing. So this one gives me what? Mq dot, which is mv, which is just what we regularly know because this is a simple system, classical system. Not classical, I mean just a particle, mv, right? So because of this, I know this is equal to mq dot times q dot minus half m, not mq dot, yeah, minus half. So what is this? Half mq dot square. So the Hamiltonian is half mq dot square, which is correct because it is the, I forgot to say that, and usually it is equals to the kinetic energy plus the potential energy. We already discussed Hamiltonian before. That is what used to determine the evolution of the quantum system, right? And I usually just say, it's the total energy, right? And this is, we did not prove it, but that is what it is, right? And indeed, the total energy of a free particle is half mq dot square, half mv square, right? Which is half mv squared. I just want to use this generalized coordinate, so later you can plug it directly to the circuit, right? Instead of v. So do not just treat P equal to mv. It just happened that P equal to mv in this case. Then what is the equation of motion? Let's take a look here. Right? Negative partial h partial q equals to P dot. Look at this. Negative partial h partial q equals to P dot, right? So what is P dot? Partial h partial q equals to what? This is h. What is the partial derivative on q? 0, because it only depends on q dot, right? So this is 0. But maybe, do you still remember the rate of change of momentum equals to? Energy. Force. F equal to ma. Again, this is F equal to ma, right? No. I should say, that's right. Yeah, F equal to ma, which is equal to mv dot, right? So it's P dot, right? Okay, this is the rate of change. In a more general sense, is F equal to the rate of change momentum if my mass is increasing actually, right? Like general relativity, right? The mass can be, I don't know, the total. Maybe I should not say too much. You keep saying I keep saying something wrong. But the point is, No change of the momentum, right? No change of momentum means it's running at a straight line. Okay? Same as what we discussed before. How about another equation, which is the velocity equals to partial h partial pi. This one is, maybe I did not put it here. We need to do some conversion. No need. Partial h partial pi, this equation, partial h partial p, right? What is this? Equals to q dot. I think here I run into problem. This equal to q dot. What is partial h partial p? Oh, sorry, I completely messed up one thing. I'm very sorry. Did not look at my cheat sheet. What is the fundamental variable for the free particle for Hamiltonian? It's P and Q, right? I should not use Q dot. Fundamental variable for the Hamiltonian, what is that? P and Q, not Q and Q dot. So I do it wrong, right? So I convert it to the wrong direction. I'm sorry, I hope that this can be an education for you in the positive way. So I still have this, I still have this, but now I actually need to eliminate Q dot instead of eliminating the P. Okay, so I did something wrong, right? So what I'm going to do, just redo it. Should eliminate a Q, but here it tells me that on the right, again, I use this equation. It tells me P equal to mq dot, so Q dot equals to P divided by M, right? Because P equal to mq dot, right? So this Q dot equal to P divided by M. Is that okay? And because of this, instead of putting this one, I want to substitute this with P times P divided by M. I keep the P, Q dot becomes P divided by M. Make sense? And for this part, I need to do the same thing because I don't want to see the Q dot in Hamiltonian. It becomes P divided by M squared. Okay, so this is P squared divided by M. This is half P squared divided by M. So what I get is no M, right? P squared divided by 2. No, what did I do? Is that right? No, P squared divided by M. Right, which of course in the classical sense is still half mv squared. Okay, now then I look at this, this is still correct. Partial h partial q, I don't have q, so change of momentum is 0. But how about partial h partial p? What is that? Yeah, of course it's still equal to q dot by this equation. But what is partial h partial p? P divided by M. In our classical approach, then this is equal to V, right? So basically, it's just saying that, yeah, dx dt equal to V. So this is consistent. Okay? Just finally, this shows this is consistent. It does not give us anything new. Okay? But This one tells us that it is moving at a constant momentum. Okay, so I'm sorry for screwing this up, but I hope you learn from that very contrasted problem for you. Lagrangian, you use coordinates and generalized velocity. Hamiltonian, you need to use generalized momentum and generalized coordinates. Okay, and you need to follow the rule. I did not just say plug in with P divided by M. I really go through the equation. And this is important when you use it to solve the circuit. Okay. Any questions? Okay, thank you. Sorry for that. Then how about simple harmonic oscillator? I just want to show this one more time. Total energy, we already say that it is half mv squared. The potential energy, right, which usually we denote as V capital V, equal to half kx squared. Right. So what is the Hamiltonian by definition? It is P times Q dot minus L. Okay. And we already know what it is L. We know that L equals to, let's go back. What is L? Where's L? Half mq squared minus half kq squared, right? So as L equal to half, I don't need to go back. I'm doing too much because I know it's T minus V, right? Equal to half mq dot square minus half kq square. Right? Q is the location. And now I need to be careful. This time I want to remove the q dot, right? But again, because this is a particle, you get the same thing because partial L, partial q dot, you expect the same thing, equals to P. And of course, when you do partial L, partial q dot, what do you get? This one. Again, mq dot, right? So I know that q dot equals to P divided by M. Okay, so I do the substitution. Everything is there, it's the same. P times P divided by M for the first term. Then subtract the Lagrangian half M. I don't want Q dot again. I substitute with P divided by M squared. And then this is plus 1 over 2 kq squared. Now this is the right form for Hamiltonian because I have Q and also P. And if I rewrite it, this is just P squared over M minus half P squared over M. So this is half P squared over M plus 1/2 kq squared. Which is, again, this is the potential energy and this is the kinetic energy. Right? So after doing all this, they are still the same. But just because this is simple, this is just a class, what we usually see. So you feel that it's a waste of time. But this is the methodology you go through, the formalism. Right? So let's look at the equation of motion. We know that, let's go back to here. Partial H partial Q negative equal to P dot. Partial H partial Q negative equal to P dot, which is equal to, what is partial H partial, did I do the negative here? I somehow missed the negative, but which does not affect the result last time, okay? Because this is negative.
The negative was there. It was on the...
Oh, yeah, sorry. Yeah, you're right. It should be -0. Okay. It's the same, yeah. So, what do I want to say? So what is this? What is partial H partial Q? What is that? Huh? Partial, this is H. What is partial H partial Q? K times Q. Right? Because I differentiate Q square, right? But I have a negative, right? So I need to multiply by negative. So this is P dot, tell me that is K times Q. Still don't know what it is yet. Then I look at this partial H partial P, which is equal to Q dot. What is partial H partial P? P over M, right? Do not just say that because I know this is velocity, then it's P over M. This is for you to check, but when you do a circuit, you don't have this. You cannot see that, right? So I have two equations. I have P dot equals to negative KQ. I have Q dot equals to P over M. So I can further change this one to Q dot dot equals to P dot divided by M. I just take differentiation on both sides. Q dot dot P dot divided by M. Is that okay? And then I substitute P dot into the second equation. This is P dot, right? I substitute into here. I get Q dot dot equals to negative KQ divided by M. Right? I substitute P dot here. This is negative KQ. So this is what? Q dot dot plus K over MQ equal to 0. Again, this is the same equation of motion. X dot dot plus omega square X equal to 0 if omega equal to square root K over M. Right, so let's pause for two minutes. Right. Any questions? Is this clear? I think the main point is on this page. Lagrangian equation is given. Hamiltonian equation is given. Is the cheat sheet. How to find the relationship between the generalized velocity and the momentum is given. The most important thing, don't make the mistake I make, is that when you do Hamiltonian, everything expressed as the coordinate and momentum. Do not have this velocity there. Then just follow the rule and come up with the equation of motion of this system. Maybe let's rest one more minute, and then we go to the quantization of the simple harmonic oscillator. Okay, so the main point is this. We already learned Lagrangian and Hamiltonian, and basically you don't need to understand them. I don't understand also, you just know the math.